Log on, tune in, find out. Another good idea from Cambridge.
Now today it's my great pleasure to welcome Dr. Jennifer Wiseman, who's our lecturer for this evening. She's worked many years for NASA. She's recently been appointed as the senior project scientist for the Hubble Space Telescope at the Goddard Space Flight Center. And I noticed in her CV that she was, even when she was a student, she co-discovered a comet with the exciting name of 114P, which also is called Wiseman Skiff. I guess that's more interesting. Maybe she'll tell us how you do that with comets, if you kind of have half each or whatever, I'm not quite sure. But already obviously very involved in astronomical type things from an early age, but also someone who's very involved in the public understanding of science. And at the moment, recently she's become director of a whole program called the Dialogue on Science, Ethics and Religion, which is part of the American Association for the Advancement of Science, which is the American main organization for communicating science to the public in North America. And so it's a very key position actually for communicating not only astronomy but science and ethics and so forth. She's had previous involvement with the Faraday Institute through being filmed for this DVD film, Test of Faith, which is on our bookstore, and also being interviewed for a book of the experiences of scientists and their own personal view of their science and faith and so on. This is called Test of Faith. So please do have a look at those on the bookstore. It's a great film if you haven't seen it already, and I do recommend that. And then finally, it only remains for me to welcome Dr. Wiseman on your behalf, who will speak to us on exoplanets, life, and human significance. Thank you very much.
How do you discover a comet? Well, maybe I should start with that story. That when I was a senior undergraduate at the university where I attended in the United States, they offered a 2-week field trip for students who would like to learn about astronomy. And we went to Lowell Observatory in Arizona, where the planet Pluto was discovered. And it's still a planet, it's just a special planet. But while I was there, I was learning how to look at photographic plates. This is the era when we were still using glass plates to take pictures with telescopes, and to use something called a blink comparator, where you look at two sequential pictures of the same piece of the sky and see if anything moved between the exposures. And stars and things don't move in that short of period of time, but just over a couple of days. But something more nearby, like an asteroid or a comet, would move. And it is on one of those photographic plates that I, quite unexpectedly, found something that looked like a comet, and I didn't know exactly what it was, but I talked to the professor I was working with, and we determined by talking to the authorities who keep track of such things that it was an undiscovered comet. We went back out to the telescope and found it. I was working with astronomer Brian Skiff, so then the authorities at B named it Comet Wiseman Skiff after the two of us. And it comes back every 6.5 years, so that's the good news. The bad news is very dim, so you really have to be a professional comet watcher to ever see it. That's the science part, but this is a lecture for science and religion, so I'll tell you the religious part of that story, which was that to graduate from MIT, where I went to school, you have to have a senior thesis written. And I was halfway through the year and didn't even have a topic. So I was praying. All students pray at some point or other in their academic lives, regardless of their professed religion. And I was praying for a thesis topic, and then this discovery happened, and I ended up studying this comet and writing about it for my senior thesis. Now, all my prayers are not answered in such stellar ways, but I thought I should share that part of the story with you. You can ask me about part 2 of the story, the science side later on. There's a corollary to the comet story, which is quite interesting. My lecture tonight, however, is about exoplanets and what we are learning about exoplanets, and then where that might lead us into thinking about the possibilities of life elsewhere and what that means for us as life here on Earth. And as you can see, there is planet Earth there in the distance. I was giving some interviews about this lecture this morning over at the BBC radio studio here, and was asked by one of the interviewers there why it is that even when astronauts go into space, their primary interest is looking back at Earth, not looking out so much, but looking back. And I think that says something about us. We are very interested in our own planet, in our own home, and how we fit into this larger cosmic picture. And even as we look at exoplanets, which I'll describe for you through this lecture, we're often looking at them through the lens of, is this an Earth-like planet? What does it mean to be Earth-like? What does it mean to be a inhabited or habitable environment? An exoplanet is just what it sounds like, a planet exo, or outside of our solar system. And as you'll see, we're discovering quite a few of them now. I'm wondering if we could turn down the house lights just a little bit. You won't be able to see me as well, but that's okay because you'll get to see these pictures much better. So, we believe there are hundreds of billions of stars in our own galaxy, the Milky Way, and now we actually know that there are billions, hundreds of billions of galaxies, so the number of stars is just staggering. In our own galaxy, one star, one of these, is our sun, and so it does kind of make us wonder, are there other planets? Just like our sun has an orbiting system of planets, are there other planets in the universe? Is there possibly another planet like Earth out there? And could there be a planet that harbors life? I'm going to spend the first half of this lecture, if I time this right, talking about the status of our scientific study of extrasolar planets, where we are in the detections and the techniques and what we're finding. And then the second half, I want to get more into the discussion of the other topic of this lecture, the other part of the title, which is human significance in life, and how different philosophies and religious views in society might react if we find life or don't find life elsewhere. How does this all fit into our view of ourselves? We're not the first people to think about such things. Greek philosophers were speculating about the idea of there being other worlds a long time ago. Epicurus said that there are infinite worlds, both like and unlike this world of ours. Now, they didn't really understand, as we do, that stars are like the sun and that planets are orbiting stars. So when they were talking about worlds, they had something sort of much more exotic and distant in mind. But nevertheless, he said, we must believe that in all worlds there are living creatures and planets and other things we see in this world. So that was pretty imaginative all the way from 300 BC. Fast forward several centuries, hundreds of centuries, and we see that medieval scholars were also thinking about this. Islamic scholars were thinking about this. Giordano Bruno, one of the church leaders, said that there are countless suns and countless Earths all rotating around their suns in exactly the same way as the 7 planets of our system that they knew at that time. The countless worlds in the universe are no worse and no less inhabited than our Earth. Also pretty imaginative and courageous, perhaps, or foolish to say such things, because, as you know, Bruno was burned at the stake. Perhaps not for this statement alone, but for being a little bit too freewheeling in his thinking. We have the advantage now in our lifetimes of superb technology that's helping us to explore the universe and actually see and detect things that could only be imagined or even couldn't be imagined before. This is the Hubble Space Telescope that I work with. It's a NASA partnership with the European Space Agency, but astronomers from all over the world use the Hubble. It's in orbit around the Earth. It's been there for almost 21 years now in orbit, believe it or not. And it orbits the entire Earth every 90 minutes, and it sends back marvelous images. Just a couple of years ago, we did the last astronaut servicing mission to the telescope, installing new instruments that are performing superbly. So just a little background on the history of astronomy here and the increase in our sensitivity. We start in this modern era with Galileo's observations about 400 years ago or so, and he was the one, of course, who figured out that the objects moving around Jupiter were there and were moons, and sort of figured out that the whole idea of orbital motion pertained to our solar system as well. And this confirmed a Copernican idea that we are in a sun-centered solar system. Then eyepieces began to be developed, improved, and through, as you see, through the 17th and 18th centuries, telescopes began to improve by the larger sizes of their apertures, allowing better and better imagery. And then we get to the 20th century with the invention of photography and then electronic detection, which allows us to take deep images, deeper than our eyes can see, by integrating the light over long periods of time. You'll notice the sensitivity improvement on the left side of the graph here is increasing on a logarithmic scale. So we're going many orders of magnitude in increases in sensitivity throughout the history of this technology. And then more recently, we have the Hubble Space Telescope launched into space, and we also have other space telescopes that are doing very well in different wavelength bands. And then SM4 there on the right is this last servicing mission that we did that put in instruments that improved the sensitivity of Hubble even more so that it's off the charts. Okay, so we are now pulling back incredible images from Hubble and other images as well. The science of exoplanets is being done with telescopes on the ground as well as in space, depending on their capabilities, to help us in this whole field as well as all fields of astrophysics. So planets we've known about for a while. We knew for a long time that we had bright planets in the night sky. Mercury, Venus, Earth, Mars, Saturn, and Jupiter have long been known to be wandering the night sky. There's some more up-to-date pictures of them. Then we have the moons of Jupiter by Galileo. And this is what excited me about astronomy in the first place. When I was growing up, we were getting the first images back from the Voyager spacecraft that was sent out in the solar system to send back images of our solar system planets and their moons. And I thought that just getting to see and imagine what it would be like to be on these fantastic and varied moons of other planets was one of the most interesting things I could ever imagine. And one of the most wonderful things humans have done is to send out these kinds of probes. I thought then, and I still think now. We have the discovery of moons of Saturn in the 17th century. And then later we find some of these outer planets, Uranus, Neptune, Pluto in the 20th century. And then now we're finding all kinds of other asteroids, more moons around planets, and what we now call dwarf planets such as Pluto. When we started discovering rocky objects bigger than Pluto out in the same belt area where Pluto is, a new category had to be defined, and so we call these objects dwarf planets. But exoplanets themselves are a rather recent discovery, and I won't go through all the history here, but the very first purported detection of a planet around a very odd object called a pulsar, which is basically a star that has outlived its main central lifespan and become a very odd object, was discovered, almost in the realm of 20 years ago. The first detection actually turned out to be a false detection, but the technique of seeing whether a star wobbles due to an orbiting planet proved to be very fruitful. And in the years since, planets have been discovered by the hundreds. I won't go through the pictures here too much, but you'll see on the bottom is Jeff Marcy and Paul Butler, who've been responsible for hundreds of detections due to finding stars wobbling due to the pull, the tug, the gravitational tug of orbiting planets. And we should congratulate them on this work. The year of discovery on the bottom here shows you how many planets are being discovered per year and how that is basically skyrocketing. So we have the early detections of ones and twosies down in the beginning of the 1990s. And then as the techniques were honed, we get more and more planets detected, mostly by this radial velocity method of seeing stars wobble. I'll talk a little bit more about that. And more recently, as in this year, we are starting to get many reports of detections by the Kepler satellite, Kepler telescope that is in space, and I'll discuss that a little bit as well. But you see what's happening here. How do we detect these exoplanets? Detecting exoplanets is a detective problem because it's very difficult to find a small, dim object that doesn't radiate visible light on its own next to a very bright star that's full of radiation that can be something like 10 orders of magnitude brighter than the reflected light from the planet, and the planet can get lost in the glare. So how do we find these planets? Well, as I mentioned, one way is to look for the tugging motions on the star that's caused by the mutual gravitational attraction of the planet and the star. It causes the planet to orbit around the center of mass, and it causes the planet to wobble around that same center of mass. You can also look for starlight dimming when a planet transits or orbits along our line of sight, and I'll show you what I mean by that. And of course, what we really like to do is take pictures or image exoplanets. That's the hardest thing because you have to suppress the bright light from the star in order to separate out the planet. So again, I mentioned that Marcy and Butler are the team that have been credited with finding hundreds of exoplanets by looking for stellar wobble. They've used ground-based telescopes, in this case the Keck Observatory on the upper right there, to do much of this confirmation, as well as telescopes in the southern hemisphere. What is done is to look at the Doppler shift of the light from stars to tell that they're wobbling in the radial direction along your line of sight. So here's our scientist looking at the star, and as the scientist looks at the star, when the star is wobbling sort of away from us, the light, as it's coming toward us, we receive it at a stretched out wavelength due to the relative motion of the star or the source and the observer. And likewise, when the object is moving toward us, because of this relative motion, we receive the light at a blue shifted frequency or a shortened wavelength. So if this is happening in a periodic fashion, you can tell that this star is wobbling. And what's being shifted? Well, we're actually looking for specific spectral lines, frequencies of lines from things like hydrogen in the starlight that we can actually measure very precisely how their frequency is shifting as the starlight goes back and forth. There's a little bigger picture of the kinds of things that we're looking for when we look to wobble. We can also try to find the wobble if it's wobbling more along the plane of the sky instead of along our line of sight. If there's a component in that direction, we can try to measure the precise position of the star and see how that's wobbling around. This is called astrometry, measuring positions of stars very precisely. And that's been done as well, not with rulers, but you get the idea. Okay. And notice how happy the star is to be measured. Okay. There are telescopes proposed that would do this much more precisely from space through a technique that's called interferometry. These would be future telescopes, but it would be very helpful to us in the science of exoplanet detection if we could build such telescopes in the future. Here's what a wobble would look like, and does look like. This is a measurement taken from the ground of a large stellar motion. And you can see how the sort of circular and rotating motions here indicate that something is tugging on that star or causing it to orbit around a particular point. The third way that we would really like to find them, as I mentioned, is blocking out the light from stars and actually being able to take a picture of the planet. This is imaging, and we use something called coronagraphs sometimes to look at things around the outside of stars. Coronagraphs were invented actually to look at the outer atmospheres of the sun. That's what they're called, coronagraphs. You block out the sunlight and you can see the outer atmosphere of the sun, the corona. But now we use them also to study outer regions of other stars and stuff around stars, like debris and hopefully planets. So again, it's kind of like putting a shade in front of the star, although it gets very complicated because light has a habit of bending around things and still wreaking havoc, even if you're trying to block it out. But you see the happy planet there down in the lower left, who's quite happy to come out of the glare. We are also, both in Europe and in the US, telescopes are being proposed for the future that would use this technique of light suppression to give us a better handle on imaging planets. Just move on from there. Okay, what kinds of planets are we detecting, though, using the techniques that we can already use? Well, mostly we're detecting very large planets because they're the easiest ones to find. So the planets discovered so far are closer in mass to Jupiter, but we would, of course, like to find things that are kind of like Earth. You see the difference there. That makes a difference in our ability to detect them. And again, imaging them is hard because stars are very bright. Here's a pictorial image of how stars are 1 billion times brighter than a planet. You see the little firefly up there? And so it is kind of like trying to find a firefly, I don't know what you call them over here, a lightning bug or a firefly, hidden in the glare of a lighthouse. Okay? So that's very hard to do, but we are doing it crudely. This is an image from the Hubble Space Telescope, which actually shows one of the very first images of an extrasolar planet. Now, I forgot to ask for a pointer, but I don't know if anyone has one of these, but it's okay if we don't. This ugly-looking thing in the middle is an image taken with Hubble using its coronagraph, which I told you blocks out starlight, which would have been where that central little dot of light is. That's where the star would be. The rays of static coming out are just an optical leftover from this crude technique. But that ring, that outer ring over there, is actually real. That's a ring of dust around the star Fomalhaut. And buried in that ring, oh good, thank you so much. Buried in this ring, well, first of all, it was thought that there might be planets in this system to kind of create this ring in the first place, to make a kind of sharp shape of this circumstellar dust emission. But lately, by looking at images taken of this system with Hubble over several years, you can actually pull out, buried in here, an object that is orbiting at just the right rate to be a planet orbiting the star. It's the first crude image of an extrasolar planet. I should pause just a moment and say the disk emission itself is an important part of studying how they form. This is an image of a young star being formed. You can't see the young star. But young stars, as they form, tend to eject jets, and the contours here are of a radio telescope map of this disk-like emission around a very young star. This is my own research. And what's important here is studying how, when baby stars form, how this disk of material eventually evolves into a planetary system. So this is a whole hot topic now, ranging from how young stars form to how planetary systems sustain and thrive. The same year that Fomalhaut image came out, another image of a 3-planet system was also released in HR 8799, again through coronagraphy and actually being able to image crudely for the first time 3 planets, gas giant planets. We're living in a very exciting time to be able to look at what was only imagined up until just a few years ago. All right, these are crude images, and this is where the science is going, I should say, in the future, is to make this better and better so that we can see not only fuzzy images of giant Jupiter-like things, but to see sharp images of Earth-like things. That's what we hope to have in the future. We're not quite there with our technology. But there are other techniques now to be able to study extrasolar planets. Another one is this transiting method I talked to you about, where planets orbit in front of their parent star. And when they do that, you can learn several things. Over here in the left, you see how the light, the total light from the star is up here until the planet blocks out some of it, and then you get a dip in the light curve. While it's dipping, you can tell from the amount of dip how big the size of this planet must be to cause that much drop in starlight. And you can also see, as the starlight passes through the outer atmosphere of this planet around the edges, you can see what kinds of emission are absorbed by the atmosphere of that planet. And that tells you something about the atmosphere of the planet, whether it has one and what's in it. There's a telescope right now using this method called Kepler, which I'll talk a little bit more about, and detecting hundreds of planets. Here's a nice pretty picture of what this looks like. Whoops. It's not working. Oh, here we go. Again, we have total light that dips when the planet goes in front and then goes back behind. Same idea, but here you get a nice image of what a star is really doing. It's churning in its upper atmosphere. So Kepler is a telescope in operation right now that's finding planets through this transit method. It is staring at something like over 100,000 stars, just staring at them to see which ones of them have this periodic dip in brightness. And it's been operating now for almost 2 years, something of that nature, and is now coming out with some very significant results. Remember, it takes a while to compile statistics, which is what it's designed to do, because, for example, an Earth-like planet around a Sun-like star would take 1 year to do one transit, one orbit, one full orbit, including a transit around its parent star. If you want to be absolutely sure what you've seen, you need more than one orbit. And of course, we're looking at stars and planets around all kinds of stars, not just Sun-like stars, and planets in varying orbits. So it takes years to compile statistics. But that is what Kepler is designed to do, and it's starting to release some very interesting results. Some of the first results that it did showed something very odd. These are some of the first planets that it detected. These are the light dips as the planet transited in front of the star. But what they found was that the orbital periods for these planets were extremely short. Now, of course, those are the first kinds of planets that Kepler was likely to find in short amounts of time. But can you imagine planets doing their entire orbit in the matter of a day or 2 or 3, whereas for our Earth it takes 365 days. So these are planets very close to their parent star, orbiting very fast, and large gas giant objects. They're called hot Jupiters because they're hot and they're gaseous and they're close to their parent star. Later on, all different kinds of planets have been detected, and I'll talk about that. But just to review, these ways of finding and characterizing exoplanets that are being used right now include this radial velocity method of finding stellar wobble by seeing the red-shifted and blue-shifted motions of the stars. Transits by seeing a starlight dims periodically. Microlensing, which I haven't talked about, but when a star and planet system is in front of a background bright star or galaxy, as the foreground star and planetary system moves in front of that background bright object, you can get distortion of the background starlight due to gravitational distortion and bending of the light. And that distortion depends on the kind of planetary system, kind of star and planet system you have in the foreground. So this is you might even consider somewhat exotic, but it actually works to find the statistics of some kinds of exoplanet. Imaging, I told you about, is when we want to actually be able to take images of the stars by blocking out the starlight if we can, at least some phases. Of course, the planet, you only see some phases of the planet as it's orbiting its parent star. And then astrometry, watching the actual motion of the starlight. Okay, I mentioned that we have hundreds of planets detected. Now, the way Kepler has added to this is by adding hundreds of more candidates to this field of planets that have been detected through this radial velocity technique by transits. But when you discover a star that's varying in its brightness, like Kepler does, it really helps to have a confirmation by using a ground-based telescope to go back and see if you can actually see that star wobbling as well. If you can see both a transit and confirm that that star is wobbling, that's a confirmation that you've actually found a planet and not something just completely unusual about the variations in the star itself. So Kepler has discovered, and there have been confirmation of hundreds of planets, but there are over 1,000 candidates that have yet to be confirmed through this ground-based radial velocity method. Also, the sizes are getting smaller and smaller, the kinds of planets that are being detected. So you see here early on, we were seeing planets that were many times the size of Jupiter. So this is a Jupiter mass right here. And now, as the years go by, we're seeing planets smaller and smaller and smaller, even 1/10 of the mass of Jupiter, even just getting down to Earth masses, or Earth sizes, I should say. So things are improving in this realm too. Of course, we'd like to see all kinds of planets of all sizes, and we're getting there. The largest ones are almost stars. We call them brown dwarfs. When we get to a few times the mass of Earth, they're called super-Earths, and here we have Earth-sized things. All right, so what has Kepler found, this new satellite that I've talked to you about? Well, it's found things, and this here is the radius of the Earth. And you'll see that most of the things that it's found are Earth size or a little bit larger, but not terribly different. A few things in the realms of Jupiters and Neptunes. And I say sizes because that's the thing that transits are best able to be used for, is the size of the planet. And mass is taken inference of something else, inferring the density of the planet or measuring some other measurement that can tell us what the mass of that planet might be. Super Jupiters, Jupiters, Neptune seem to be the most popular out there. Super Earths, and so far, Earth's about 6%. Here's a look at some of the sizes of things that have been seen. You see that they're huge. Some of the first Kepler planets, the easiest ones to detect, are huge compared to Jupiter and certainly compared to Earth. But they're getting better and better at seeing things. These are radii of the Earth here, so just a little bit larger than Earth here. And interestingly, there's been a recent press release where they have announced that they found dozens of planets that are in what's called the habitable zones of their stars, which I'll talk more about. But also that they are finding at least many systems that have multiple planets. So everything that says Kepler 11 here are planets around one particular star. And in this case, these planets are all pretty tightly wound in near orbits around their star. So that's an exciting system as well. So this system, compared to our own, looks kind of like this. And 5 of these 6 planets are close and tight, within the orbit of what would have been Venus in our own solar system. So that's an interesting detection as well. And remember, they're finding out all of this just by watching the variations in the starlight. They're seeing these planets as they transit and inferring that these are multi-planet systems. So that's an artist's conception of what this system would look like. Now, these planets also interact with each other as they orbit. They have gravitational tugs on each other. So clever scientists have figured out that if you know that a planet is transiting, you found it transiting, and you find that the timing of when it enters its transit and when it exits is a little bit off or a little bit delayed or accelerated, you can figure out that other planets must be tugging on it, and you can do all kinds of computer calculations, and that tells you something about the relative masses of these planets, how much they tug on each other. And they've used that and other techniques to make estimates of even the masses of these objects and find that they believe they are objects that have kind of a light and fluffy outer zone, maybe around a more dense core. I think it was mentioned that some of these planets are like marshmallows with chocolates in the middle or something like that. You can go on and try to infer exactly what that composition would be. And here we have some of the planets that have been found, and where these Kepler 11 planets, these are the B, D, C, E, F planets, where they would fit in a graph of the size of Earth versus their mass. And so you see kind of objects that you have to infer from their mass that they might have both hydrogen, helium, and a rocky core with some sort of outer fluffiness in them. It's very difficult to do this kind of analysis right now with the kinds of data that we have. So the fact that they can even speculate to the composition of these things is a tremendous achievement. So just the cover of Nature came out this year. This one system, Kepler 11, is surprisingly flat. It has 6 planets. These inner planets are very closely spaced. They are not too much bigger than Earth, and they have low densities implying a mixture of solids and light gases. I think this is an astounding conclusion just from looking at the dimming of stars. So we are now beginning not just to detect planets and kind of count the numbers of them, but to characterize them, not in great detail, but we're trying to understand more about them. As I mentioned, their mass, their composition, their densities, their orbits, this kind of thing. How do we do some of that? Well, it's the science of spectroscopy is important here, and that is being able to look at the light from a star as it's absorbed by the planetary atmosphere, to then infer what that planetary atmosphere must be made of. So Hubble Space Telescope has a spectrograph that's been used on some of these transiting planets to infer that the planetary atmosphere has things like sodium, carbon, hydrogen, and oxygen in the atmosphere. That was one of the first exciting exoplanet characterization studies that ever came out from Hubble around a famous system, or it's famous to astronomers, called HD 209458b, which is the planet. I'm going to move through this a little quickly, but as planets do eclipse, we are now finding that they have molecular emission as well. So not just these atomic gases, but it's possible that we are seeing molecules, methane, water, carbon dioxide, carbon monoxide, all done through this eclipsing technique of transits and seeing what kind of light is absorbed through the atmosphere. And I'll show you what this looks like in a spectrum. This is taken with a Spitzer space telescope, which is another space telescope that observes in the infrared. And here is a theoretical model in the blue here of what the spectrum should look like if there were water vapor in the atmosphere. The yellow crosses here are the actual data, and so there's not a whole lot to work with here, but the data actually does kind of fit along what you might see if there were absorption from water in the atmosphere. So the more absorption, the higher it is on this graph. And you see that here in infrared light, you do see something that's consistent with water vapor in this exoplanet atmosphere. Now, if you look with the Hubble Space Telescope NICMOS camera, at slightly shorter wavelengths, still in the near infrared, you see this water curve, again modeled in the blue here. But now the data points, which are bent differently, but you see them kind of in the black here, don't follow this water curve very well out here. You have to add other things, in this case methane or ammonia, other molecules into the model to get it to fit the data better. And so this is so crude right now, but it's basically showing us that it's likely that these planets have multiple molecular as well as atomic components in their atmospheres, just like our own atmosphere does. We can also find out from the timing of transits other things. In this case, Hubble's ultraviolet instrument called the Cosmic Origin Spectrograph found out that for one of these transiting systems, the timing of the transit started earlier in ultraviolet light than it did in visible light. There was a slight delay for the visible light to start its transit when you compared the two kinds of data. That seems to imply that the outer atmosphere of the planet, which is hot and you see in ultraviolet light, is being, in some sense, tidally disrupted and stripped off by this the star to which it's orbiting very closely. So you can even infer that kind of atmospheric disturbance by looking at the timing of these transits. And then finally, from the science point of view, what we want to find out about signs of life. So one of our highest goals in astronomy is to find out from our technology whether there are Earth-like planets, and that's hard to define what Earth-like is, but whether there could be, in fact, signs of habitability or even inhabitation, signs of life. And scientists, astronomers are mostly looking for what we would call biomarkers, or the science of astrobiology, looking for signs of basic biological processes. But of course, there are also groups looking from the other end, looking for intelligent civilizations and listening for information in that way, such as the Search for Extra-terrestrial Intelligence program. If our goal is to find planets with evidence for life, then the ones we've discovered so far are not really great candidates, and I think I've mentioned why in many cases. This is a picture of our solar system. It is not to scale, okay? But it shows you something that's nominally known as the habitable zone. This is a region that's not too close to the parent star and not too far away, and that could potentially allow liquid water to exist. And we think liquid water is the one basic requirement for life, even remotely similar to life as we know it. Now, this habitable zone can vary because it depends also on the atmosphere of the planet, whether there's greenhouse effects, what kind of ellipticity of the orbits of the planets, all kinds of things. It's a notional effect. But still, we're finding planets now that are, some of them are in the habitable zone, but some of them are much too close to their parent stars to have liquid water, and some of them are much too far away. One of the Kepler results that's most exciting this year was finding dozens of planets that are in the habitable zone of their parent star. I also mentioned that planets are relatively close into their stars, but once we are able to image them, we want to look for evidence of life. So we will look for evidence of oxygen, such as ozone, that can be produced by plants and algae. On our planet, the reason we have continuous oxygen in our atmosphere is because of the plant biology going on here. We will look for liquid water, which we might see in the form of water vapor in the atmosphere. That can be a support mechanism for life. We can analyze reflected light as well as that light coming through in absorption to see if the planet has an atmosphere in that respect. And of course, things like methane can be associated with biological activities, such as having cows, so we might find a bovine planet this way. But you also have to rule out that these things we see are not just produced by basic geological processes. Methane, for example, can be produced by some geological processes that have no biology to it. So you have to be clever about this, and the whole science of astrobiology is looking into these issues. You also have to realize that our Earth biosphere has not been the same throughout history. So we have some life forms in sort of these three branches of the tree of life that produce signatures that in our atmosphere that might be observable from a remote telescope. Oxygen, as I mentioned, from photosynthesizing organisms, methane from methane-producing organisms, and then if you have vegetation, you'll see a sharp edge at red wavelengths of light due to the nature of plants and photosynthesis that should be able to be seen if it's happening in bulk on another planet. This is what our Earth spectrum would look like if we were off the Earth looking back, presumably, and we see this by what's reflected off the moon from our own Earth. So the sunlight is being reflected off the Earth through our atmosphere and then reflected off the moon and back to us, and we'll see what we look like, and we can see evidence of ozone and this chlorophyll red edge and water and oxygen. So these are the kinds of things that we would like to look for if we're looking at extrasolar planets to see if they have any kinds of processes like we see on Earth. Looking through history, we've had primitive life on Earth much longer than we've had advanced life. So methanogens and cyanobacteria have been around since the Earth was only 1 billion years old. Now we believe the Earth is several billion years old at this point. So we have to take into account what we might see if we were to look at a planet in a different stage of life development than Earth. This is what Earth kind of looks like conceptually over geologic time from 4.5 billion years ago to now. And you see that the relative amounts of oxygen, carbon dioxide, and methane have changed. As life processes turned on, the atmosphere changed. Life processes began to produce oxygen that was visible, begins to use carbon dioxide, methane starts and then reduces. So you have to take into account the biological and geological evolution of a planet before you can figure out what kinds of biomarkers, which we call these things, to look for. We think, in summary, that life needs some kind of a surface or an ocean to thrive. Now again, you could imagine kind of exotic life, but from all we know in biology so far, we understand also that life needs liquid water as a basis. And so we want to look in these habitable zones and for water vapor. We believe that life is most likely carbon-based, and that gets into the chemistry of carbon versus similar elements like silicon. It turns out that carbon is the most suitable for building complex molecules and sustainable molecules. So silicon-based life is unlikely. That's a whole different lecture. We can search for evidence of plant life. We need carbon dioxide. We can look in visible and near-infrared spectra of light to find both molecules and atomic emission. We have to realize that Earth spectrum has not always been the same, but it has been pretty much the same for about the last 300 million years. That's about all we know right now in looking for signs of life based on what we know on planet Earth. I will just briefly say that if we want to go the other direction and think about intelligent civilizations, we might want to think about what they might be hearing from us. We know that our radio and television signals started emanating from Earth a few decades ago, and we wonder if other civilizations are hearing that, and so we're also listening to them. However, with our fiber systems now, we're not emitting so much of that anymore out into space. But there are whole arrays of radio telescopes tuned in to listen for particular signals that are intentionally sent from alien civilizations. This is run by private programs such as the SETI Institute. And these go on and on. These searches, it is like searching for a needle in a haystack and trying to guess which frequencies a civilization might use and where to look in the sky for them. I'm not dwelling on that in this lecture, but it is an interesting thing. All right, so I've gone a little longer than I hoped with that part, but I'm hoping I can still have my full 55 minutes, so very good. So I want now to move from that very quick overview of where we are in the science and the detections of extrasolar planets into the leap we might make if we actually do find life out there. Or conversely, if it looks like other planets are extremely inhospitable for life and that we might be incredibly unique here. Since this is a lecture based on the idea of discussing science and religion, it is very appropriate for us to think about how the world's religious communities might respond to the detection or the non-detection of extraterrestrial life. And we have to consider the possibilities of finding simple life, which is what we're mostly looking for right now with our telescopes in astronomy and astrobiology, plants, simple microbes. But then, of course, what about the existence of complex life and intelligent life as we measure it? What would that mean? How would society respond? Many have speculated that perhaps the whole globe would go into crisis of belief if we found life elsewhere, that maybe we would be terribly confused, that the world's religions would be turned upside down, we wouldn't know what to do. It turns out that that's not exactly what people think. Of course, we won't know until it happens, but it turns out that if you do a survey of people of various religious faiths and ask them what they think would happen to their faith if we found life elsewhere, you typically get not a tremendous amount of angst. So theologian Ted Peters did a survey. He called it his Extra-terrestrial Religious Crisis Survey, in which he asked people whether or not their faith would be in conflict with the finding of life, and particularly intelligent life, elsewhere. And so you see the quotes here from various perspectives. Islamically, we do believe that God created other planets similar to Earth. Only arrogance and pride would make one think that Allah made this vast universe only for us to observe. And then an evangelical Christian says there's nothing in Christianity that excludes other intelligent life. And a Buddhist respondent says extraterrestrials would be essentially no different from other sentient beings. They would have Buddha nature and would be subject to karmic consequences of their actions. And then a self-identified mystic says, my belief in God is absolutely unaffected by extraterrestrial life. And then the final quote here is, discovery of extraterrestrial life would not affect my personal belief system because I'm a stone atheist. I don't know what a stone atheist is, but I think we get the idea that no one seems to think that their own views will be turned upside down. However, when people think about views outside their own, they often speculate that there would be a crisis. But again, here's a sort of graphic display of this survey. The question was to the respondents, agree or disagree, official confirmation of the discovery of a civilization of intelligent beings living on another planet would so undercut my beliefs that my beliefs would face a crisis. True or not true? Agree or disagree? Most people agree that I mean, most people do not agree with this statement. Most people disagree. They do not believe it would cause a crisis in their faith. And that includes everyone from Catholics, Protestants, Mormons, Jews, Buddhists, and non-religious folks as well. Is that all there is to be said about this? Well, not exactly. I think we need to look through a little bit more of the historical thought on this. Historic Islamic thought embraced the possibility of other worlds. Imam al-Razi stated that it's established by evidence. I have to look back into the history here to see what evidence they had at that point. But there exists beyond the world a void without a terminal limit, and it is established as well by evidence that God Most High has power over all contingent beings. Therefore, He, the Most High, has the power to create 1,000,000 worlds beyond this world. And he goes on down here to be a little more sharp. The arguments of the philosophers for establishing that the world is one are weak, flimsy arguments founded upon feeble premises. This being, from the 12th century. So there were arguments about this long ago. And I am appreciative to Dr. Nidal Gassoum, who has spoken here in past summers at the Faraday Institute, for some quotes from Muslim scholars who tend to find verses in the Quran that support the idea of there being other worlds. Now, when you get to the idea of there being other human-like creatures, that's when these faiths run into a few challenges. Let's look into Christian theology. Would Christian theology embrace the idea of life on other planets, whether it's simple life or intelligent life? I think we have to do a quick review of the faith before we understand why this is an important question. So, with my sincere apologies to any of you who are theologians in the audience, this is a terribly brief overview of a rich faith. But it is a faith that I hold. So to some extent, I can speak to this from my own experience. The basic background of this faith is that creation is good by whatever means it came about, whether it was by evolutionary processes or some other way. It is good. And God is the author of it, that God loves people, and that human beings, reflect God's image. We are made in God's image. But that we are all fallen from that ideal image in relationship with God, and we need redemption and restoration to peace with God. And there are different variations a little bit on how God does this, where there's a Catholic emphasis on original sin being passed down from generation to generation. But in any case, we need God's redemption, and then the good news or the gospel is that God became incarnate. He became human to help us and to redeem us and to restore and save us into this right relationship with God. And that in some way the whole universe will shares or will share in the benefits of this redemption of humanity. Now the question comes, well, would this apply to extraterrestrials? No? We're not quite to the point of having to apply this theological question, but still it's something that has been thought about. Would alien life in the Christian theology experience this presence and redemption of God in person as God did on earth through Jesus Christ? And how would this happen? Would this intelligent life do dumb things like we do? Would they be fallen and sinful and need redemption? Would Christ appear in non-human forms elsewhere? Or does his appearance on earth fully accomplish whatever needed to be accomplished for life elsewhere? Scriptures don't tell us much of this other than the fact that there is one Savior in Christian theology, and that one Savior suffices for everyone, and however this Savior chose to do the work. So one notable verse here is that Jesus Christ, the righteous one, is the atoning sacrifice for our sins. And not only for ours, but also for the sins of the whole world. So then you have to ask, well, does this include the whole universe? You have to think. There has been thought about this. The Catholic Church has done some serious thinking about this. They held a recent conference. The Pontifical Academy held a conference on astrobiology. There were articles about it in the newspapers. I'm not sure that the Vatican would consider this complimentary, but nevertheless, it's amusing. But a quote from Father Jose Funes, who directs the Vatican Observatory, says, why is the Vatican involved in astrobiology? Although astrobiology is an emerging field and still a developing subject, the questions of life's origins and whether life exists elsewhere in the universe are very interesting and deserve serious consideration. These questions offer many philosophical and theological implications. So at workshops like this, they brought together scientists and religious leaders, and scientists who were both religious believers and non-religious believers together to talk about the science and try to tease out what the important theological issues are. Some quotes from a couple of Catholic priests there tend to conclude that there's not a terrible conflict between faith and finding life elsewhere. Father Denoya says Christians have always understood that the entire cosmos is a creation of God, that any life anywhere is a divine creation. There'd be absolutely no motive for scandal if scientists were to establish the existence of life elsewhere. And likewise, Father O'Collin said, I don't think the discovery of life on other planets would pose a qualitatively different challenge than the discovery of the New World. And I should add the discovery of the New World by Europeans who didn't know that there were already humans in the New World. It wasn't new to the people already living there. Prior to the 15th century, people had only the vaguest idea about human life on the other side of the Atlantic. Again, the people he's referring to are obviously the Europeans. Yet we survived that, and in the end, it deepened our understanding of Christ as a truly universal Savior. Well, that sounds great, but not everyone agrees that this is such a simple issue. Paul Davies, a noted scientist and a writer on philosophy of science, says that he thinks the discovery of a second genesis of life elsewhere would be of enormous spiritual significance. He says the potential challenge to Christianity is being downplayed by religious leaders. The real threat would come from the discovery of extraterrestrial intelligence, because if there are beings elsewhere in the universe, then Christians, and I don't believe he considers himself a Christian believer, I think he considers himself an agnostic, but he says Christians, they're in this horrible bind. They believe that God became incarnate in the form of Jesus Christ in order to save humankind, not dolphins or chimpanzees or little green men on other planets. So there's not universal agreement on exactly how the world's religions would respond to things. And typically people from outside religious viewpoints can see more problems potentially than people on the inside. More Catholic reflection. If personal life were rediscovered, both of these priests I mentioned before said it would require some theological tinkering as they thought about it a little bit more, especially with this concept of original sin. How can persons on other planets share in the stain of guilt derived from Adam and Eve, with whom they are most probably not descended? Yet if they don't, what exactly is the condition from which Christ has redeemed them? We'd have to work a little on this, I suppose, O'Connor said. But I think this is the key point. Anybody who thinks the doctrine of original sin is more important than Jesus being the universal Savior already has their priorities out of line. What about Protestant views? Again, most see no problem with finding extraterrestrial life, even intelligent life. Such a finding would simply reflect on the greatness and the creativity of God in most people's minds if you talk to them. Evangelist Billy Graham has been quoted as saying, I firmly believe there are intelligent beings like us, far away in space, who worship God. But we have nothing to fear from these people. Like us, they are God's creation. However, there are people who are not so comfortable with the idea. So here's a quote from a conservative Christian ministry program in Atlanta, and he thought about it and said, my theological perspective is that extraterrestrial life would actually make a mockery of the very reason Christ came to die for our sins, for our redemption. The entire focus of creation is mankind on Earth. And he went on to say, an intelligent, morally aware extraterrestrial life would undermine that view and belief in the incarnation, the resurrection, and the redemption drama so central to the faith. He believes it's a huge problem that many Christians have not really thought about. So you see there is some disagreement there on the magnitude of the repercussions of this kind of discovery. And then the final sort of realm of discussion here is if we do find life, we're finding exoplanets, if we find extraterrestrial life, is it going to affect our view of our significance as human life on Earth? Are we special? Are we unusual? Are we average? Are we significant? Are we accidental? What does it mean? Now this is also a topic of an entirely different course and exploration, but what in fact does it mean to be significant? We have to realize that you can define significance in different ways. Does it mean that you're central, that you're common or rare? Does it mean that you're long-lived or short-lived? You can think of it in different ways. In the Copernican revolution, we found out that Earth is not the center of the solar system, and we went on to understand that the solar system is not the center of our galaxy is not the center of the universe. There may be other universes even, and so ultimately, though, this Copernican science was found to be compatible with Christian faith and other faiths that thrive. So will the finding of exosolar life follow likewise? And we must remind ourselves that not being central or unique as life can be interpreted as a loss of significance if significance is based on position or rareness. But interpretations can vary. In fact, it turns out that back in Copernican times, being removed from the center was actually, in that culture, often considered an elevation, not necessarily a demotion. And I encourage you to read the works of Dennis Danielson in the American Journal of Physics. He is actually a professor of literature from the University of British Columbia who studied the culture and interpretations of centrality in the time of Copernicus. If we look to the biblical viewpoint, we find out that the significance of human life, time and again, are described in the Bible as a choice of God, not because of the significance of the length of human life or our place, anything like that. In fact, often we're reminded that we are dust. The psalmist writes, "As a father has compassion on his children, so the Lord has compassion on those who fear or reverence him. For he knows how we are formed. He knows that we are dust. As for man, his days are like grass, but from everlasting to everlasting the Lord's love is with those who fear and respect him. Praise the Lord, all his works everywhere in his dominion." So you get this idea that it's God's choice to love and reveal himself to humans, not because of their own significance in their own right. And we're not the first ones to wonder about this, though. I quote another psalm here from King David who says, "O Lord, our sovereign, how majestic is your name in all the earth." And I should remind you here that before King David was king, he was a shepherd boy. So he had lots of time to sit out with the sheep and look up at the stars and think about them. And he said, "When I consider your heavens, the work of your fingers, the moon and the stars which you've established, what are human beings that you're mindful of them, or mortals that you care for him?" So the same thoughts we're having now when we think about hundreds of billions of galaxies, he was thinking back then, just looking up at the stars. "And yet you made them a little lower than God and crowned them with glory and honor." So he, again, was coming to this conclusion that it was God's choice to give significance to his life. I found by reading literature that the presumption of whether intelligent extraterrestrials will hold religious faith or of how Earth's religions will respond to the detection of exolife seem to depend on one's prior view of religion. So as you read literature on this, you'll find statements of the sort that advanced civilizations will surely have progressed either away from or toward religious belief, depending on how people feel about religious belief on this planet, or that finding extraterrestrial life will either disturb or affirm current religious faith on Earth, depending on one's perspective of the usefulness of religious faith on Earth now. So we're all kind of looking through these philosophical presuppositions. A nice quote from C.S. Lewis, who wrote back in 1960, when people were thinking about this issue, about whether finding life elsewhere was going to affect Christian faith in particular. He says this is a warning to what we may expect if we ever do discover animal life, he says vegetable does not matter, on another planet, Each new discovery, even every new theory, is held at first to have the most wide-reaching theological and philosophical consequences. It is seized by unbelievers as the basis for a new attack on Christianity. It is often, and more embarrassingly, seized by injudicious believers as the basis for a new defense. But usually, when the popular hubbub has subsided and the novelty has been chewed over by real theologians and real scientists and real philosophers, both sides find themselves pretty much where they were before. So it was with Copernican astronomy, with Darwinism, with biblical criticism, with the new psychology. So I cannot help expecting it will be with the discovery of life on other planets, if that discovery is ever made. So, in summary of this part of the lecture, the discovery of exoplanets, and particularly exosolar life, is and will be astounding, and will likely be adopted within Christian beliefs, similarly to many other faiths, as exemplifying the greatness of God. However, the discovery of intelligent, moral, self-aware exo-life poses special consideration, especially within this Christian theology I mentioned, requiring the extension of the effects of God's personal incarnation on earth in some way that blesses all creatures everywhere. I would like to mention my own view, which is that I love discovery, and we keep being surprised in scientific exploration, and I can't think of anything that would excite me more than finding signs of life on other planets elsewhere, and that to me would be a further affirmation of my own view that God is creative in ways that we can just barely imagine. Pope John Paul said, from the Galileo case, we can draw a lesson that is applicable today in analogous cases which often arise in our times and which may arise in the future. It often happens that beyond two partial points of view, which are in contrast, there exists a wider view of things which embraces both and integrates them. So I think that philosophy may work in this realm as well. So to close here, I want to look back at our own lovely planet Earth. It is our home, and the more we think about exoplanets and find them, the more cognizant we are of the preciousness of life that we have on Earth. Right now, just to summarize the science that we're getting from Kepler, it looks like, from looking at over 100,000 stars so far, about 6% of them could have Earth-sized planets. About that percentage have super-Earth-sized candidates, which aren't that much larger than Earth. 17% have Neptune-sized candidates. They say candidates because they have to go and do follow-up studies. 4% have Jupiter-sized candidates. There's a lot of planets out there. We're finding more and more. And as we look to the future, this is a graphic, an artist's description of a new telescope coming after Hubble, the James Webb Space Telescope, which is named after a NASA administrator. The James Webb Space Telescope will be even more suited to looking for some of these extrasolar planets because it is tuned in infrared wavelengths of light where we can actually do much more detailed spectroscopy of atmospheres of planets. This is a conceptual idea of what a spectrum might look like taken with the James Webb Space Telescope of a planet that has water and carbon dioxide. It's a model. But this telescope is being developed right now. It should be launched later this decade, and we can look forward to further exoplanet characterizations of this telescope using planetary transits, as well as all the discoveries continuing through the other methods that I mentioned. And we also hope for a future telescope where we can take advantage of those coronagraphs, where we can take more images of planets and study them that way. So again, JWST will give us our first opportunity to really detect for sure and confirm liquid water, not just vapor water, but liquid water on transiting super-Earths. This quote, I think, is where I think our heart should be, the excitement of Thomas Wright of Durham in contemplating this idea that there might be other suns, other stars with inhabited systems. I think instead of thinking about the problematic ways that we as society will have in digesting the idea of life elsewhere, I think we, including those of us of religious faith, can have a sense of true excitement. So I like this quote because it's kind of what we call a back of the envelope calculation. He was contemplating this idea of many suns that he read about in Paradise Lost. And so he started thinking about this. He said, now admitting the breadth of the Via Láctea, that'd be the Milky Way, to be at about 9 degrees, and supposing only about 1,200 stars in every square degree, there's going to be about 3,888,000 stars in that area. And all of this, then he realizes you have to extrapolate that. So he says all of this is just a minute portion of the great expanse of heaven. And then it dawns on him, these numbers of stars. He says, what a vast idea of endless beings must this produce and generate in our minds. And when we consider them all as flaming suns, progenitors, primum mobilis of a still much greater number of people worlds. So now he's talking about intelligent life. What less than an infinity can circumscribe them? What less than an eternity comprehend them? What less than omnipotence produce and support them? And where can our wonder cease? That's the kind of reaction I think we ought to have when we think about these things. And this truly is my last slide. Looking back at our own planet Earth from the space shuttle, after it had serviced the Hubble Space Telescope, it looked back and saw this image of Earth as the sun was just rising or setting. So you can see the Earth, the sunlight shining through this very thin layer of atmosphere. We see how fragile our planet is by how fragile our atmosphere is. It's such a tiny, tiny part of our sphere of Earth. We're privileged to live on this planet. We need to take good care of it, even as we're learning about how life may thrive elsewhere. I'll close with that, and I thank you very much for your attention.
Thank you for a fantastic lecture. I wonder if I could just flip the attention onto the vast majority of the universes. Hello. I wonder if we could flip attention to the vast majority of the universes which cannot be habitable. Because whether or not there are lives out there, you've shown that that can only be in a tiny minority of the exoplanets. So, what do you think God's relationship is with all of these non-habitable places? Do you think they exist because you have to have a lot of them just to generate the small proportion of places that life might exist and have a relationship with him? Or do you think God has a place in his heart for all the places which cannot be habited?
Well, first of all, I think I didn't want to give the impression that we know the percentage of planets that are habitable, because we don't. We are just, what I've showed you this evening are the baby steps toward understanding other planets and what might be needed for life there. So these are very crude attempts to match the conditions on other planets to what we experience here on Earth. I'm not sure we're at the point yet where we can say that the vast majority of planets would not be habitable, for the simple reason that planets can have moons. So even if you have a big gas giant planet, we don't quite understand how intelligent life could live in a gas giant planet, but it could possibly live on planetary moons. Planetary moons can perhaps harbor life under ices or in various conditions. We don't know the statistics very well, so I'm not sure we can say yet whether or not conditions on other planets are overwhelmingly too harsh for life, or whether there might be more hope for it. We're not quite there. There's also an issue of trying to understand the stability of planets. So even if you have a planet where life could potentially live, if planets are most commonly being bombarded by asteroids very frequently, and as we look to other star systems, we are finding that many of them have heavier amounts of dust and debris than our own solar system does, which means those planets are getting bombarded much more frequently. There may not be time for advanced life to evolve and thrive. And so even if you get life, it might not have the chance to make it, as we've seen on our own planet's history, when we get bombarded, it takes a big toll on life and sends it in a different direction. Those things aside, your question still remains, what would be the purposes from a theological perspective of having uninhabited planets? I don't know, I'm not God, but I do think that that it may be the case that planets themselves are wonderful objects that glorify God in their own existence, even if they don't have life. I mean, we look at, Uranus is a beautiful planet, and Venus is a beautiful planet, and Mars is an interesting planet. And so we're not to judge, I think, the value of objects in space by whether or not they harbor life. On the other hand, it may be the case that it takes this kind of, depending on your view of the role of evolutionary development of the universe, it may take all kinds of systems and all kinds of conditions before some of them can actually produce conditions that are conducive for advanced life. So you may need this large number in order to get some fraction, or maybe just one, that has the chances for life as we know it. We don't have enough data yet to answer that question from a scientific point of view. So.
Please, yes.
If I may ask a philosophical rather than scientific question, thinking back to the quote you gave from Billy Graham, that there may well be many other civilizations who are worshipping the same God that we worship. If we met them, how would we know they were worshipping the same God?
Well, that's a good question. First of all, meeting them is a hard thing, because as you start realizing the distances between star systems and the chances of one civilization being able to actually, just because of the laws of physics, being able to travel and meet another civilization, it becomes difficult within our human lifetimes, virtually impossible to have that kind of interaction, which is very disappointing to all of us who grew up watching Star Trek or other things. But that aside, let's say that we had some opportunity for an exchange of information with an intelligent civilization. How would we know whether they have a religion? How would we know whether they worship something? How would they know whether they worship the same God that we do? I have no idea. But I think, from our own theological perspectives on Earth, and now let me again transition to the sort of specific Christian theology with which I'm most familiar with, we can say that God is in charge of whatever is out there, and God has covenants with different types of creatures here on Earth, so we can assume that God has some sort of covenant, we may not know what it is, but with other beings as well, depending on their needs. So even on this planet, we have in our Bible descriptions of God's desire to, for example, provide food for the animals, that He's worked out, an arrangement for now that animals will, in some sense, be dependent on humans for good or for ill, but that in the end, when humans are redeemed, that the animal will share in that glorious redemption. So we get little hints that God has some sense of communication with other creatures on this world. We can only assume, again, from within a Christian viewpoint, that God is having the same kinds of covenants with other realms of creatures of which we haven't had the need to know, so we haven't been informed.
We're going to just take one more quick question, and then we'll have to stop. Please, in the middle here.
I think that in fact we ought to be very interested in. I think we ought to be very interested in life in other worlds nearby. In fact, we can possibly find it. But surely, statistically speaking, you can't deny that there must be life somewhere else in this galaxy or in the universe. And it's almost inconceivable that it could not have arisen elsewhere.
Right, so there are two things kind of working against each other right now. One is that we've been a little disappointed in recent decades as we've looked in our own solar system. We looked on Mars, we haven't found life, we haven't found evidence of life yet on any other planets in our own solar system. The jury is still out on whether the moons of Jupiter and Saturn might have primitive life, maybe buried underneath ice. So our expectations of finding civilizations on Mars and on the moon and all that have been dashed through recent decades through scientific study. And as we look through to other planetary systems and young star systems as they form, which is what I study, it does appear that conditions for many planets that we're starting to find would be very harsh for life as we know it. Either the planets are too close to their parent star, they're too hot, or the star itself might not be such a hot star, but then to have liquid water, you'd have to be very close to that star, and then you're getting all the dangerous cosmic rays and things that are just, impounding the planet, which makes it difficult for intelligent life, for advanced life to evolve. And then, as I mentioned, you have planetary systems that look like they are, for the most part, embedded in thicker dust and debris, perhaps than our own solar system, so that planets are getting constantly bombarded, which may make it difficult, again, for advanced life. So a lot of things, I don't think we have enough data to know whether life is unlikely or not. But the flip side is just as you say, even if it's incredibly difficult for life to get started, or even if it's started for it to thrive and exist and advance, well, the numbers are enormous. We have hundreds of billions of stars and hundreds of billions of galaxies, so even if the probability is extremely small, you would have to think that you can never rule it out, right? There must be, and whether you're looking at this from a strictly scientific view or even a theological view, you could say, why wouldn't God have produced a universe abundant with life? That's kind of my feeling. The problem, though, is that it's going to be hard for us to detect this life and to detect these civilizations. So even if they're out there, even if we assume that the universe is teeming with life, and even intelligent life, it's very hard for us to make contact because of the distances involved. The first thing we're doing is looking for simple life, as I described in the lecture, looking for evidence of biological activity. That's probably the most we can hope for in the near-term future. Being contacted by an alien civilization, that would be exciting, but it's something we can't quite predict. And going to these other planets ourselves is a little bit out of our technological realm.
We only can look at such a small sample.
That's right, that's right. So there's no telling, given this enormous number of stars, many people assume that there just must be other civilizations, other life, because of the numbers. It's just hard for us to confirm that scientifically. So.
Okay, well, all this talk of life is making me think about refreshments, I have to say. And I think
carbon-based refreshments.
Which we will do in just a moment up the stairs around the back there. But first of all, I think we really want to thank Jennifer Wiseman for a fascinating lecture.